Hi, this is Moser with a quick tutorial on writing electron arrangement in noble gas notation. So, noble gases. Well, okay, first let's see what you should be able to do. After watching this video, you should easily be able to write the electron arrangement for any element in noble gas notation. I promise to stop doing that, but it's just so much fun. You already need to know how to write electron arrangement in orbital notation and electron configuration notation. Obviously, you need to know how to find the number of electrons for any element and how to draw the subshell filling diagram. Well, that said, what's so special about noble gases? What are they anyway? Where are they? Where are they? Where are they? There they are! The noble gases are the group 18 elements, and they're called noble because they're unreactive, just like the nobility wouldn't have associated with peasants and riffraff. Well, the noble gases don't associate with any other elements. They are stable and satisfied because of having a full octet and their uppermost occupied main energy level, and therefore they're completely non-reactive. We use the noble gas notation as a shortcut, so let's look at what noble gas arrangement means. Let's start with our very first noble gas. In the first period, group 18, we have helium with a 1s2 arrangement. Next comes neon with 1s2, 2s2, 2p6. Argon, 1s2, 2s2, 2p6, 3s2, 3p6. And krypton, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Whew! We'll stop there for right now. Other than helium, which of course only has one main energy level and one subshell, but that subshell is full, when we start looking at neon, we start to see what makes the noble gases so stable, so noble. For each noble gas, if we look at their uppermost occupied main energy level, we notice that there's a full S&P on the uppermost occupied main energy level. What's another word for uppermost? The electrons that reside on the uppermost occupied energy level? You've probably heard it before. Valence electrons. That's right. And remember that all elements seek stability by getting what we call a noble gas configuration, meaning they have a full S&P subshell on their uppermost occupied main energy level. Well, that's what we see here in the noble gases. Well, that's pretty cool, but how does that help us to write electron configurations for other elements without losing our minds? I'm glad you asked. So let's just locate neon on the periodic table real quickly. Here it is, and there's the electron configuration. And we know that as we move, starting with hydrogen, across the periods and down to the next period and across the period, every time we move over one, we add one proton because the elements on the periodic table are ordered by their number of protons. Well, because of what we know about the number of protons and neutrons in any element being equal, that also means that anytime we move over one, we add an electron. So let's write the electron configuration for sodium, which starts off the next row, the next period. Okay, 1s2, 2s2, 2p6, 3s1. Great! You notice anything? Right here, enclosed in the electron configuration notation for sodium, that sure looks an awful lot like neon. So what we can do is shortcut this by writing the electron configuration for sodium as follows. Everything neon has plus 3s1. Oh, that's pretty slick. If we want to write magnesium with 12 electrons, well, we know that that's 1s2, 2s2, 3, oops, geez Louise Moser, 2p6, 3s2. Or we could translate that. Everything neon has plus 3s2. Wow, that really is a neat trick. So we can do this for any element on the periodic table because we end each period with a full uppermost occupied main energy level S and P orbital, well, except for helium. Which means we can look to the next row, the next period, and say in each case that it's whatever this noble gas has plus the next 1, 2, 3, 4, whatever number of electrons, wherever they're filling. Now, it takes a little bit of practice on this, and a lot of people will start out still needing to write the electron configuration notation. But once you get good at it and once you learn some tricks from the periodic table, it's very simple. Let's practice one or two together. Let's look at vanadium, atomic number 23. So this has 23 electrons. Well, for any element, to figure out which noble gas we would need to use, we would go ahead and look to the period above it. So because vanadium appears in the 1, 2, 3, 4th period, and the 3rd period noble gas is argon, vanadium's noble gas configuration is going to be written starting off with, well, it's got everything argon has, plus 1, 2, 3, 4, 5 electrons. Okay, so argon plus 5 electrons. We can't write that. Well, we know that argon ends with a full S and P on its uppermost occupied main energy level. And we see a pattern, if we look carefully back at those noble gases we wrote, that helium, which is in the 1st period, has an uppermost occupied main energy level of 1, and neon, in the 2nd period, has an uppermost occupied main energy level of 2, and argon, in the 3rd period, has an uppermost occupied main energy level of 3. So if I know argon ends on the 3rd period, and I know that it has a full S and P, I know that the last subshell that argon would have filled would be 3p, which means those 5 electrons that I'm adding, well, I'm going to start with 4s2, that's that, and then I still have 3 electrons left to fill. That will be 3d3. That was pretty easy. Now, until you get really proficient with this, you'll probably still need to write out at least the orbital notation for the noble gases. But I promise you, as you gain skill and gain fluency with this, it'll get easier and easier and easier. Go practice!